Yeah.
Do I have to repeat that whole thing? Oh, it changed the format of the screen. Look at that. Wow.
So I have a question for the prelims.
Yep.
So the question will be from medical biochem that you taught, the part that you taught, and then the physical biochem, right? Or the molecular biochem. So it's gonna be from everything that you taught, first semester, second semester.
Everything I ask is from this class. I mean, the hemoglobin question, you could have answered most of that from medical biochemistry.
Yeah.
Because I teach that in medical biochemistry, but it's really geared towards the level that I teach in this class.
Okay.
Okay, which is a little more advanced than what I teach in
medical biochem.
Yeah, because we can go into details in that prelim question, but I expected more than just med biochem. A lot of times what I teach, two simple sort of broad areas, and you'll see that in other questions that I ask: binding and thermodynamics. Enthalpy, entropy, free energy, binding. Binding affinities, how do you convert that to a free energy? Vice versa, how do you think about binding problems? What methods would you use to measure binding? Those kinds of things. And we're going to be getting into even more of that now when we do this coming week, diffusion and sedimentation and some examples from the literature, because that's what we're going to do next. But all of the stuff that we've already done on binding is relevant there. The next question I send you, which I'll probably give you on Tuesday, is related to something called entropy compensation, which we have only talked about generally, I think, but that will come up now in a lot of what we talk about. Okay, is that enough, Jelaine?
Yes, Dr. Goria.
Okay, so what I was going to do was, yeah. Okay, so problem 5 is from this older Van Holt, and one of these are the questions right here. So 3 is one of the questions. It's asking for the second virial coefficient for bushy stunt virus. And in general, people that I've looked at are doing it, quote unquote, more or less correctly. Is this going to let me write on here? Yeah, I don't want to copy. No, that's not what I want either. Well, it may not let me write on here. Tools. No, home. File. I don't want that. I don't want that. Well, it's not going to let me write on here. Why is it not going to let me write? Huh. I may have to do this in another way. That's just going to give a yellow. I don't want that. Take that off. Ah. Okay. So it's a sphere. And so you immediately get you immediately know for a sphere, it's 4 V bar over M. If you don't know, that's what you should know. Okay. That formula is in my head because I learned it in a book called Tanford, and it's in this Van Holt issue. The problem is that they give you the radius, and so a lot of you think that this is calculating the volume, but that's not what V bar is. The units of V bar are milliliters per gram. The units of V bar, it's the change in the volume as you add something to a solution while holding all other components constant in units of milliliter per gram. This is a virus. Do you know what kind of a virus bushy stunt virus is?
No.
It's not
Anybody?
orange.
It's an RNA virus. It's a spherical RNA virus. That's correct. So it's composed of a capsid, which is the protein, and RNA. Okay, so I don't know what the proportion is. We would have to look it up and see what the molecular weight of the RNA is. That's the molecular weight of the whole virus, if I understand it right. So that's 10 million. So what fraction of it is RNA and what fraction of it is protein? So what's a typical V bar for a protein? Can anybody tell me? 0.73 milliliters per gram. Can anybody tell me, so this is protein. Can anybody tell me what the V bar of RNA is? It's typically around 0.55. Okay. That's a little bit more mysterious. The V bar, I remember I showed you the program SetInterp, and I showed you that SetInterp calculated V bars. The V bars for proteins comes from the sum of the V bars of every protein amino acid times the number of that amino acid in a sequence, summed over all, divided by the V bars. And so basically, this one is easy to calculate because it depends upon the amino acid composition. And every amino acid has a slightly different V bar. This is not always true. It's close to being true. Remember that software paper that I gave you that calculated extinction coefficients as the sum of tryptophan, tyrosine, and disulfides? Well, it's a similar sort of software package. SetInterp will calculate this as well. So this is usually calculatable, and 7.3 is an average. It's 7.2 to 7.5. It can vary with what's bound to the protein. So other stuff like nucleic acid, a GTP, ATP binding site, or salts, or any kinds of things can alter this. Experimentally, it's usually the V bar that we calculate that we use, but we can measure it too. DNA, RNA, when you experimentally measure them, they're surprisingly insensitive to the salt. And by salt, I usually mean sodium and potassium. And they're usually around 0.55. So many people have measured this. I don't know that we'll talk about those papers in this class, but I could, put those papers in your hands if I needed to. So this probably is the average. Okay, it's probably not this. There's probably more protein than RNA, but in general, I would say it's about the average. It might actually be 20% RNA and 80% protein, and you would have to correct for that if you knew it. And so that's what the V bar is going to be. It's going to be 64 or something. And then the molecular weight is given, and that's how you calculate it. This is the volume of one molecule. Okay, because that's the R of one particle. What you're looking for is units of milliliter per gram. So that's what you're really looking for. Okay. All right. So if you didn't do it that way, I took points off already, and I will take points off. And so that's what you really need to be aware of. I think it says that in the section in this chapter or in a previous chapter where V bar comes up. The second question is number 3, and this has to do with percent deviation from ideal behavior. Okay, And the thing that you sort of need to know is how you would calculate that. And so it gives you this, okay, which is sort of a way of calculating partial specific volume that you then convert to that equation up there for a sphere. But this is now giving you different formulas, okay? And so it's asking you to use different formulas. The thing to look for in thinking about this, how you calculate deviation, is this table up here, because that's what this is. This is saying it's 1.5% deviated from ideal at 5 mgs per mil. The question down below is changing the concentration. I think it says 3 mgs per mil down below, because it's concentration dependent, how much it deviates, okay? And so that's what you calculate. The 1 is the ideal, and this ends up being multiplied times the ideal form of this equation. And then it's B M2, which is the molecular weight. The 2 just simply refers to whatever the macromolecule is. And then the concentration in mgs per mil, okay? And so whatever these units are, that's the form of the equation. And it's showing you that random coils are 25% non-ideal, and that long rods can be as much as 37% non-ideal at 5 mgs per mil, et cetera, et cetera. And so that's the form of the equation. What you need to do is figure out the proper equation for B based upon the description. A hard sphere, so it's that formula. An alpha helix of the same density, a rise over run, and a helix radius of 3 angstroms. So this is essentially a rod. Alpha helices will not run indefinitely as a rod, but it's giving you a dimension. It's giving you the diameter, although it's giving you the radius, and alpha helix of the same density. Oh, it's giving you the molecular weight up above. So given the molecular weight, you know what the alpha helix is. You have to calculate how many residues might be here, and then how long it might be, and what its width is. And the formula, if you don't know it out of your head, I think I did this the other day, is L over D V bar over M. So that's what this one is. This one ends up being over here. And then you plug this in with 30,000 and 3 mgs per mil, not 5 mgs per mil, to that equation up above. Yeah?
Yeah.
And again, if you didn't calculate using the right V bar, then maybe your percent deviation is going to be odd as well. Yeah? Okay, what was I think I asked number 5. I think it's 5. Yeah, osmotic pressure data. And so it's basically calculate M sub n. So it's basically using the equation in this chapter that plots osmotic pressure versus concentration, and you can get the number average molecular weight from that type of calculation. This is giving you, I think, what you need in terms of interpreting the number average. This is just giving you sort of a single point, I think. And so you can plug the numbers into the formula, and then this is giving you a plot where you have to extrapolate and get the number average molecular weight from the plot. So I'm not going to go through that unless you want to ask questions about that, but those of you who turned it in already sort of did that. Yeah. One of the things that, yeah, some of you show me the plot on the page, etc. Okay. And what was next? Is 6? It was 6 and 7. Yeah, it's 6 and 7. So this is again giving you data for the number average, but then it's also getting the slope of the plot because you're getting the slope out of
Dr. Correa, is MN and MN bar is same?
yeah.
Yeah, that's what I was confused with, because I tried to find that in your lecture PowerPoint as well, and I was confused with it, that
Well,
MN.
so is it up above here that they show number weight and Z average? Okay, and so what they mean is that it's an average value in terms of number or in terms of concentration. That's what you end up
Okay.
using down below. And
Yeah.
the bar is sort of an average value if it was a mixture. So you would have, if there was more than one component. So it might be the number average if there's some kind of a mixture in the solution. Often a sample isn't pure. And so
Okay.
notice this is a fraction of polyvinyl chloride in methyl ethyl ketone. Okay, so it's a fraction.
Okay.
All right, and so these polymers are almost never single size. They're a narrow range of, and so what you're going to get out of this is an average value.
Mm.
Okay, and so that's why he's putting down the bar, because it's an average of this fraction. So you take some kind of a cut. It might be a solubility cut. It might be a cut, a fraction off of some kind of a separation column that has fractionated certain size distribution of the polymer. So that's why the bar is there, because it's not a pure component. This is not a protein or a clean piece of a restriction fragment in a clean piece of DNA. Does that make sense?
Yeah, it does. It does make sense.
And that's why we introduce the average. And so if you were then to study this protein, this polymer, excuse me, remember we talked about this when we went over this. I realize that was a long time ago. That if you have a mixture, if it's homogeneous, then these are all the same. The number, the weight, and the Z give you the same number. If it's a heterogeneous solution, then the number will be less than the weight, will be less than the Z. So you'll get different answers, and you get different answers depending on what technique you use. So here we're using osmotic pressure. Osmotic pressure, that's a colligative property. And so colligative properties give you number average molecular weights, because colligative properties are sensitive to numbers. Weight average would give you a slightly different number for this because it's dependent on the weight concentration. But the average would end up being a little bit different. And then a Z average has this molecular weight squared term in it. And so it tends to emphasize the bigger stuff in the mixture. So it usually has a bigger value than the weight. If they're not equal to one another, then that tells you that it's heterogeneous. Okay, the other way this is often displayed, if you were doing this by some methods that we haven't talked about, there's often something called polydispersity. And polydispersity, often off of molecular weight or sizing column data, often if it's less than 1.1, we'll consider it homogeneous. The polymer guys use this terminology. I don't tend to use this terminology because I tend to work on proteins and DNA molecules or RNA molecules that are pure. But if it's less than a polydispersity of 1.1, within error, it's homogeneous. I can actually see stuff that's 1.01. I can pick up that fraction of contaminant by the methods I use. And so I don't consider this homogeneous, but the polymer guys do. And they can pick this stuff up as well. They can see the differences between number, weight, and Z. And so they would know about this. So I don't think any of you guys went through a polymer program at Southern, but the polymer guys at Southern would know this kind of stuff and would think about this kind of stuff. Okay, that a lot of this ends up today being talked about in the polymer field, because our techniques today allow us to really isolate pure molecules. Okay.
Yes.
And then this one, I think some of you are still working on this. This problem was challenging, but it's the same thing, right? They're asking us for B and 1 plus BMC for a 1% solution. The thing here is, when I went over this in class, they're asking for excluded volume plus the Donen effect. Right, so there's two formulas that you have to know, and you're doing both of them. In one case, you're assuming all of the DNA is charged and there's no salt screening going on. There's no Debye screening going on. And then you assume that 80% of the charge went away. And so the Z squared, this has a Z squared term in it. And so the Z squared in A is 200 squared, and in B, it's 40 squared because it's 80% reduced. And part of the problem may have something to do with the form of the equation. And are you using M in the denominator, not M squared? And what you find is, when you do the final answer, is that excluded volume is the dominant term, but and it's still the dominant term in salt when you have this exclusion, but it's much smaller and closer to the excluded volume term. So the charge term ends up being the major term. If your protein is close to isoelectric, then it goes away. Okay. So is there anything that we need to talk about this? You have any questions?
No, I had issues with number 6. Now I'm a little clear. I'm going to work on that.
Okay.
And I think we had one extra question for assignment 6.
Yeah, it was just the showing that you could take the derivatives in two ways. There's a perfect differential, right? And so I think you get the same answer if you take the derivatives. Were there any questions about that?
No, I'm good with that.
Okay, so Jelena always speaks up. Anybody else want to speak up? Are we okay?
I'm okay with Jelena being our spokesperson.
Okay, Jelena, you're in charge. All right, let me talk about one other thing. If I close this, it wants me to save the writing. Yeah, and so I'll save the writing. Let's see. I said something wrong the last time we met. I know that's hard to believe. Where are we? It was electrophoresis. And here's the lectures. Right here. Lindsay asked a question and I made up an answer. And the answer is a lot more obvious than what I said. Ascending, descending. I made something sort of up, but I wasn't thinking very clearly, obviously. When you start this way, where's my pen? Show up. Is my pen going to show up on here? There it is. When you start this way, this boundary is going up. That's ascending. This boundary is going down. That's descending. You're getting two sets of data from the same experiment. Okay. And the reason that ascending and descending don't have exactly the same appearance is obviously that gravity somehow affects this. There's more sort of mixing or stirring or interaction with the walls And it's different if you're going with gravity than against gravity. And so that's why the shapes of ascending and descending are slightly different. Okay. Ascending is slightly more sharp than descending. Okay. So I think that's a clearer answer than whatever I made up the last time when Lindsay asked a question. All right. The other thing that is worth saying, you don't have to really do this if you don't want to. I think I can close that. Sure, save it, close it, go here, go here. If you Google Tiselius, his name is Arn. I told you he was Swedish. I think I told you that much. What I didn't tell you is this guy actually won the Nobel Prize. Okay, he got the Nobel Prize in 1946 for his research on electrophoresis and some other things, but really he was the guy who invented electrophoresis. The thing I would want you to be aware of that, again, this is not an assignment. You're welcome to do it. And I'm not sure it's here. What I'm looking for is his Nobel Prize lecture. Because when these guys give a lecture at the Nobel Prize, you know that there's a ceremony held. It's actually published. And so I think that's actually it. You can see it's December 1948. Okay, and so they actually publish his lecture, so you can see what he thought he was famous for. It's not unusual for people to talk about more than just what they get the Nobel Prize for, because it's usually sometime after they do the work and they've moved on to other things. I'll tell you this again later, but you could actually go read what his work was and large molecular weight substances. So he was using, and by large molecular weight, he simply means, I think, proteins, because up until that time, people weren't always working on protein complexes. Okay, so you can go find people's Nobel Prize lectures. I'll probably show you another one in a couple of weeks. So that's number 5, and I said we would not go over time here. So
That was assignment 6.
Number 6. Number 6. Yeah,
oh, that was
I'm
6?
about to say.
Yeah.
Okay, I'm sorry. That was number 6. Right. Okay, there you go. And so few of you have turned in number 7. So I'm not sure we're ready to talk about number 7 is the problem.
I have a question from number 7.
Okay.
Yeah, I will turn in numbers 7 and 8 this weekend in Dr. Korea. It's been.
Okay.
Okay.
What's your question?
I'm having trouble with 15.7.
Uh-huh.
I don't know if it seems very simple, but for some reason I'm making it very complicated.
Well, it quote unquote is simple. Of course, all of these questions are simple if you know how to do them. So the thing is that remember when we derived oxygen binding or ligand binding to make a complex? Maybe it was monomer enmer. And we sort of showed that there were multiple ways of deriving it. You could do it one at a time. A plus A goes to A2. A plus A2 goes to A3, etc. Or you can do it 3A goes to A3. 4A goes to A3. So what we showed was that there were multiple ways of doing it, but then we also showed that they were equivalent. And the difference was is that the overall K is equal to the product of the stepwise Ks. Do you remember that? You should go back and look at it, okay?
Yeah,
But-
it's very vague, but I do remember it.
So it's a similar sort of thing here, because what they're doing is they're showing you that you can make dimers with 2 monomers, and then you can make a tetramer with 2 dimers, or you can make a tetramer with 4 monomers. Okay, and so the K4 there is just now going to let me write again. I'm going to have problems with this. Stop it. And we're back into the pin. There we go. Thank you, pin. Okay, and so 4P goes to P4. And so this is what he's calling K14. All right, but K24 is 2P2 going to P4. So this is K24. All right. And so 4P is going to P4. You could either go directly to P4, or you can make 2 dimers and then go to P2. And so the way you sort of have to do this, 2P goes to P2, okay, but you need 2 of these. And so you basically have to show that K14, let's see if we can do this, P to the 4th, so that's K14, okay, so K12 is P2 over P squared, and K24 is P4 over P2 squared. Okay, I'm not putting parentheses in here, so this may be a mess. All right, times this, but I need 2 dimers. So I've actually got to take the K1 to K24 twice. Okay, I've got to do K12 squared times K24. Okay, and so that has to be squared, and this has to be to the 4th power. It's squared, so that's to the 4th power. So when I multiply this out, that and that cancel, and I get P4 over P to the 4th power, which is that. You see, and so K12 squared times K24 is equal to K14. And so what the table is doing is it's giving you numbers. Under different conditions, I guess. I don't think I have that part of it copied here. Yeah, I don't have it copied here.
There was
But-
a section that was left out there.
Yeah, but what it's doing is it's giving you some numbers, but then you can use those numbers to calculate the other numbers. Does that make sense? So remember the whole thing about thermodynamics, path independent. And so you can make tetramers 2 ways. You can just bring 4 monomers together, or you can make 2 dimers and then bring them together. And the overall equilibrium constant should be the same if it's a true equilibrium. Okay. And so the K14 will have odd units. It will be m to the -3 if you're doing this in molar. M to the -3 will be the units. The units of this are inverse molar. And the units of this, oh, and then we do 2 of these. And then the units of this are also m to the -1, but we do 2 of these. And so these will sum up to m to the -3 because this will be squared. so that the units match. Okay, so K14 will be a big number potentially. It'll be 10 to the 18th. And this will be 10 to the 5th, and this will be 10 to the 5th, but then squared, this will be 10 to the 10th, and this will be then 10 to the 15th, and they'll be in the right ballpark. You see that? Okay, does that help?
Yes, that helps a lot. Thank you.
Okay. All right, so we're at 11:49. I'm getting a message that I'm at a meeting, but I don't think that's my meeting. I know it's not my meeting. Okay. What else? Is that good enough for now?
Yes, Dr. Correa, I'm gonna get you my homework 7 and hopefully homework 8 by this weekend.
Yeah.
Yeah.
You're okay. Everybody's on schedule. So let me show you one thing real quick. I'm playing around with the schedule because I'm always sort of making this up as we go, depending on what advance we make. So this is where we are today, 4/8. This is us. On Tuesday, I'm going to start lecturing on diffusion and sedimentation. This is the same chapter that we did electrophoresis from, but it's the first couple of parts. The first part is diffusion, the next parts are sedimentation, and then it went into electrophoresis. So I always tend to do electrophoresis first, and now we're going to do diffusion and sedimentation. We probably won't get through all of that in one session. And then at the end of the next week, I'll then start talking to you about some applications, and I'll show you some applications so you get an understanding of how we actually use these methods to solve problems. Right now I have a plan. I'm not sure that it's going to work. I usually cover these papers in this next week, the third week coming up, because these talk about sort of, I would call them advanced sort of applications. 2 of them are Timoshev papers, and one of them is one of my papers from 20 years ago. But I want to show you some other things. And then what I'm going to do in here as well is show you some software. In the past, I've actually made you log into software, download and log into it. So here's the problem. It's a PC software package. It runs in DOS. It runs in Windows 10. It does not run in Windows 7 anymore. We've made it so complicated, it no longer works in Windows 7. So that's already a problem potentially, unless all of you have a Windows 10 machine or access to a Windows 10 machine. It also doesn't run on a Mac unless you have some kind of Windows software installed. So you have to have, so I think a couple of you are Mac users, and so that would be a problem for you. I run it on my Mac, but I've installed some software. So that's also a bit of a problem. So I'm gonna still show you some stuff, and so there'll be some demonstration stuff to show how we use this software. The book stuff that I'm talking about is, I would almost call it pictorial. We don't plot data any longer to get values. We fit data to get values. We fit raw data. And so I'll talk to you about that when we get into it. Okay, so I don't have the PowerPoint posted yet, but you know what chapters we're going to be talking about on Tuesday. As a matter of fact, I'm not sure that I have the folder even published yet. I probably don't. And the reading is coming out of the book, so you have to use your copy of the book. I won't move the book into the Canvas folder because you already have it.
Yeah.
Any final questions? All right, on Tuesday, we'll set a time to do this again next week, okay? All right. And as we go through this, we'll get better at it. You'll get better at it, and maybe I'll even get better at it. I don't know. And we'll see if we can help you make some progress. I'll also give you another example of a prelim question. Okay?
That sounds great. Thank you, Dr. Correa.
All right. Bye.
Yeah, thank you, Dr. Korea. Have a good week.